Okay, this is that gas, and this gas is combined gas. This is a video lecture over the combined gas laws and Boyle's, Charles, and Gay-Lussac's law of gases. The quote that we have is, "The falsehood has an infinity of combinations, but truth has only one mode of being." So, what were the goals for this lecture? What we're trying to figure out, students will be able to explain the terms isothermal, isochoric, and isobaric. Just knowing the definitions of those and being able to relate what equation goes with isothermal, isochoric, isobaric. And number two is to use the equation below to calculate volume, temperature, and pressure. So here's our combined gas law, and we're going to use that equation to calculate those variables. So, what we already know, what we've talked about, that pressure is of the molecules striking the container. So as those molecules hit the container, they impart a force per that area and they create that pressure. Temperature is related to kinetic energy of the molecule. So as the speed increases, the temperature increases, and volume is the space the molecules can disappear in. So that's the volume is going to be the space in between the molecules in the gases that we have. What we should have learned from the lab, that number one, by decreasing the temperature of a gas, it decreases the volume of the gas. We looked at that, and decreasing the temperature decreases the pressure exerted by the gas, and increasing the pressure on the marshmallow decrease the volume. So we looked at all of those different aspects in the lab by looking at all of those different variations. So let's look at all of them and look at volume, temperature, and pressure, and how do they affect a gas. So gases are continually changing pressure, volume, and temperature. So what we look at is what changes occur to the gas in and on the outside of an airplane as it takes off. So if we look at an airplane, it goes from a very normal pressure to up in the air 35,000 feet, and we see that the pressure will decrease. How does that affect the volume and the temperature of the gases inside the airplane, outside the airplane, and as the collision strikes? And what do we have to do to make sure that all the passengers are safe? So the way we look at all of those combinations is all those different things is we look at the combined gas law equation. It looks like a big equation. There's a lot of variables, but it's kind of repetitive. So the pressure P1, so the initial pressure, V1, which is the initial volume, and T1, which is the initial temperature. So that would be the airplane sitting on ground level. That's the initial pressure, volume, and temperature. And then as it climbed to 35,000 feet, what we would see is that the pressure on the airplane would change, and we would get that that would be our second pressure, and then we would have our second volume and our second temperature as everything increased and it changed. And so basically what we do is this is just how those affect a gas. So if we change the pressure, what happens to the gas? If we change the volume, what happens to the gas? If we change the temperature, what happens to a gas? And so we're just looking at all those three things together. Pressure, both of them measured in millimeters mercury atmosphere, kPa, psi, all of those units, all the standard units that we have. One thing I'll note is that your P1 and your P2 have to have the same unit. Okay. Initial volume and final volume have to have the same unit as well. And then we always use the unit of Kelvin to do any type of math. We use Kelvin, we don't use Celsius, so make sure that we're converting all of our Celsius temperatures into Kelvin. And this is the combined gas law equation. So let's jump into an example. It says a sample of a gas is collected over water at 23 degrees Celsius. The partial pressure of water vapor is 21 millimeters of mercury. The gas has a volume of 50 milliliters and the pressure of 1.09 atm. It says the question is, what is the volume of the dry gas alone at STP? So what we use to kind of solve for this is it's kind of what we use in physics, and it's kind of a preview of what you'll see, is we use the guess method. So it stands for given unknown equation, substitution and solve. And so basically what we do is we set it up and we look at what we're given. So in our first given, what we see is that we have a temperature. So we're just going to label that as our T1 is 23 degrees Celsius, but remember we need it in Kelvin, so we add 273 to it and we get 296 Kelvin. Okay. The next thing we see is we see the partial pressure of water vapor. Now we should take this into consideration. Remember, anything that's collected over water has that partial pressure of water in it. So what we have to do is we have to subtract the water vapor pressure because it wants the volume of the dry gas. So we got to take that water vapor pressure out. And we see that this is in 21.1 mmHg, millimeters of mercury, and this is in atmospheres. So we got to have a conversion there. So we just go ahead and we have 21.1 mmHg, set it up, 760 millimeters of mercury equals 1 atmosphere. We go ahead and we work that out and we get a partial pressure of right around 0.028 atmospheres. And we just subtract that from our original pressure, so that 1.09. So our P1, which our initial pressure, is going to be right around 1.062 atmospheres. Okay, and then it gave us a volume, which is right here, which is V1, which is 55 milliliters. And so this is our given. It also gives us something else. It says, what is the volume? So we're searching for volume of the dry gas at STP. Now remember what STP means. It means standard temperature and pressure. So our standard temperature is always our 273 Kelvin. So we'll go ahead and write that down. And it's changing. So what is the volume of the dry gas at STP? So we're changing it. So that is going to be our T2. Is 273 Kelvin. And then we also have a standard pressure, which this pressure is in atmosphere, so I want my standard pressure, my P2, to be in atmospheres as well, which is 1 atm. So this is our G, which is our given. Our unknown, what are we solving for? We're solving for volume as it changes to STP, so we're solving for V2. That's our unknown. Our equation that we're going to use is the combined gas law. So our P1 V1 all over T1 equals P2 V2 all over T2. Okay. Now with this, what we'll do to kind of solve it out and get it before we substitute it, cross multiply. So I get my P1 V1 T2. So it's just these variables times that, and this variable times that. And it equals our P2 V2 T1. Now remember, what are we solving for? We're solving for our V2. So we go ahead and divide both sides by P2 T1. And we get our equation that we're going to use. So this is the actual equation that we're going to use, already solved for V2. Okay, so all we have to do is now we just have to substitute everything in and then solve it. And so what we'll do is we'll take it and take all of these variables and plug it in. So make sure that we're plugging in the right things at the right spot. So our P1 is going to be our 1.062 atmospheres, ATM, times our V1, so that just went out, times our V1, which is 55 milliliters, times our T2, and that's the thing here, so that's 273 Kelvin, all divided by our P2, which is 1 atmosphere, times our T1, which is 296 Kelvin. And we go ahead and when you're plugging this in the calculator, just go ahead, put a parentheses on the top, parentheses on the bottom, and go ahead and plug that in, and we will get an answer right around 53.87 milliliters. Okay, moving on to our next example. It says a sample of oxygen has a temperature of 78 degrees Celsius, a volume of 7.8 liters, and a pressure of 408 millimeters of mercury. If the sample was moved to a room with a temperature of 21 degrees Celsius and the volume of the container was increased to 9.9 liters, what is the pressure of the container? So we use our guess method, write down our given. So our given is going to be temperature, the first temperature we see, which is 78. Remember, we need it in Kelvin, so we add 273 and we get 351 K. Our V1, which equals 7.8 liters, and our P1, which is 408 millimeters of mercury. And then we're moving it to a room, so our second temperature is 21 degrees Celsius, but we add 273 and we get 2.94, but 294. Okay. And a new volume, or V2, of 9.9 liters. So that's our given. Our unknown, it says what is the pressure of the container. So we're solving for our unknown is going to be our P2. Our equation is the combined gas law, and we'll go ahead and solve it for P2. So we have our P1 V1 all over T1 equals P2 V2 all over T2. Cross multiply, P1 V1 T2 equals P2 V2 T1. Then we go ahead and solve for P2 by dividing both sides by V2 T1. Those cancel and go away, and there's our equation. Okay, so all we have to do here is just plug everything in. So we take all of our stuff, we plug it in. Now make sure we don't, the tendency is to mess up on switching the temperatures. Make sure we keep that and don't switch them up. So go ahead and plug it in. Our P1 is our 408 mmHg, and that equals or times our V1, which is 7.8 liters, all times our T2, which is 294 K, all divided by our 9.4 liters times 351 K, and that will solve for our P2. Go ahead, check, make sure that we got all those right. And then we plug into the calculator, parentheses on the top, parentheses on the bottom. Go ahead and work that out, and we'll get something right around 269.25 mmHg. Alright, so the question is, does pressure, temperature, and volume change every single time? So in the combined gas law, what we saw is that, yes, in those situations, pressure, temperature, volume, they all were changing. But there are some situations, like what we looked at in the lab, that something's held constant. And what we have is we have three definition terms here. We have isothermal, isobaric, and isochoric. So in an isothermal situation, temperature is held constant. So we could look at this example when we looked at the marshmallow and the syringe. When that happened, what we saw is that as it was, the pressure or the volume decreased, the pressure increased, and what we saw is that the temperature didn't change, the room didn't change. And so what we saw is that the temperature was held constant, but what happened was we pushed the marshmallow in the syringe and the pressure increased. Isobaric, the pressure is constant. So when we looked at the crushing of the soda can, what we saw is that it crushed it because the pressure was constant, but the volume changed and the temperature changed. And these are like when we have reactions that is open to the atmosphere. The atmospheric pressure never changed in the room, but what happened was the volume of the can decreased because the temperature decreased. And then we have isochoric, which is volume is constant. We could look at that as the egg was going into the flask, and then we saw an example would be a bomb calorimeter. Basically what we would see is that the volume didn't change. That flask didn't change its volume. What happened was the flask had a decrease in temperature, which decreased the pressure. And so all those situations that we have, that sometimes a variable is held constant. And in normal equations, in normal situations, what you'll see, like in problems, is that you're only given two of the variables and one of the variables missing, or it says that this would be the temperature, but it's held constant. And so anytime it's held constant, what we can do is we can take it out of the situation, or take it out of the combined gas law. So isothermal, let's look at that first. Temperature is held constant in an isothermal situation. It was confirmed and published by Robert Boyle. And what happens is when somebody publishes an equation, publishes their finding, they usually get named for it. And it's very useful when examining pressure and volume in an insulated environment. So we can look at how things react in a very insulated place. And so since it was confirmed and published by Robert Boyle, we call this Boyle's law equation. But it's very simple. Since temperature is held constant, it can be taken out of the equation. So when we look at the combined gas law, we have our P1 V1 all over T1 equals P2 V2 all over T2. Since temperature is held constant, we can literally just erase it from the equation because it's not going to have anything to do with the rest of the equation. And this is how we get our Boyle's law equation. Now you do need to know that Boyle's law is Boyle is related to this situation when it's isothermal. It's good basic level questions there, developing questions that you can have. When we're looking at it, the one thing that I would make sure that we write down about the equation is that pressure and volume are inversely proportional. So what we saw in the lab is as we decreased the volume in the syringe, the pressure increased. So that's what inversely proportional means. As one goes up, the other goes down. So as pressure went up, the volume had to go down. And if our volume would go up, our pressure would go down. It's still using this equation right here, and it's just our P1 is initial, V1 is our initial volume, and then we have our P2, V2. Making sure everything's in the same unit, that's very big. Keep it in the same unit. So let's work our first example about Boyle's law. It says a sample of nitrogen gas is placed in a syringe and has a pressure of 1.2 atmospheres and a volume of 55 milliliters. What is the pressure of the nitrogen gas if the syringe is compressed to a volume of 25 mils? Okay, so we use our guess method. We write down our given. We have a pressure 1, which is 1.2 atmospheres, and we have a volume 1, which is 55 mils. So we write that down. Our P1 is going to be our 1.2 atm. Our V1 is our 55 milliliters. And then we look and we see that our changes the volume, so our V2 is going to be 25 milliliters. Okay, so our V2 is 25 mils. Now our known, we're solving for our P2. So our P2 is our unknown. We're trying to figure it out. Now everything's in the same unit, so we can go ahead and move on to our equation. Now since it doesn't talk about temperature here, we don't see a temperature in the problem, and it's a syringe, we can see that, and there's no temperature, doesn't say standard temperature or anything else, it's constant. So we just use our equation P1 V1 equals P2 V2, and we just go ahead and we solve for our P2, which we go ahead and take that, and that will just be our P1 V1 all over V2, and that will be our P2. So we plug everything in, and what we'll get is our 1.2 atmospheres times our first volume of 55 mils all over 25 mils. Okay, solve that out. After we substitute everything in, solve it out, and we'll get a second pressure, or our pressure will change to 2.64 atmospheres. Now we can check, and just after we get our number, we'll see, does that number make sense? Well, what happened to our volume? Our volume decreased, so our pressure, since they're inversely proportional, our pressure should increase, and we see that our pressure did increase, so that number makes sense, and we move on from there. Now, isobaric. Isobaric is where pressure is held constant. This was first published by Gay-Lussac in 1802, and he credited the discovery to Joseph Charles earlier in history. Joseph Charles did some work and led Gay-Lussac to publishing it. And so what we see here is that it's going to be credited to Joseph Charles. It's useful when reactions are in open vessels. So since the pressure is held constant, the atmospheric pressure is not going to change as the reaction's going on. It's really good for us to use there. So we look at Charles' law equation. Well, how do we get this? Well, again, since our pressure is going to be held constant, we look at our combined gas law, P1 V1 all over T1 equals P2 V2 all over T2. And remember, pressure is held constant, so when it's held constant, we just erase it from the equation. And there we go. There's Charles's law. Okay, one thing I would write down here is that volume and temperature, they are directly proportional. Okay, so as one goes up, the other goes up. As one goes down, the other goes down. If we increase the temperature, we increase the volume. As we decrease the temperature, we decrease the volume. Still using our same units, we have our initial temperature, initial volume, final temperature, final volume. Make sure here that our temperature is always in Kelvin. Remember, if it's in Celsius, we have to convert. So let's go ahead and work an example using Charles's law. Okay, we have a 912 milliliter sample of helium is placed in a balloon at 21 degrees Celsius. So we see that this would be our V1, this would be our T1. And it says if the temperature drops to 10 degrees Celsius, so T2 temperature of 10 degrees Celsius, what is the volume of the balloon? So let's write down our given, and remember these are in Celsius, so what do we have to do? Convert them to Kelvin. So our V1 is going to be our 912 milliliters is our given in our guess method. We write down our given, and then our T1 is going to be, after we convert it to Kelvin, we add that 273, we get 294 Kelvin, and then our T2, remember, add 273, we get 284 Kelvin. Okay, we're searching for, it says, what is the volume? So our unknown is our V2. The equation we're going to use is our V1 all over T1 equals V2 all over T2. Okay, to do this, anytime you see fractions, just to make it easier on yourself, anytime you see a fraction, cross multiply. So we get V1 T2 equals V2 T1. Okay, now when we have that, we'll go ahead and solve for unknown. Our unknown is going to be V2, so we divide both sides by we divide, our unknown is V2, so we divide both sides by T1. Almost messed up there. Okay, so this is our equation. Go ahead and substitute everything in and then plug it into our calculator and solve it. So we do our 912 milliliters times our T2, which is 284, all divided by our T1, which is going to be 294. We go ahead and plug that into a calculator, and we get V2 equals our 880.9, and that would be our milliliters. Now we check and make sure, does this answer make sense? Well, remember that volume and temperature are directly proportional. So what happened to our temperature? It went from 294 to 284, so it went down. So it would make sense that our volume would also go down. Now, the last situation that we have is isochoric. That is where volume is held constant. This was originally discovered, but giving credit to Gay-Lussac, and it kind of still holds the Gay-Lussac name to it. It's useful when reactions in a closed vessel. So we have a closed vessel, we have something that's not going to change its volume, and so it's useful in that. We use it in bomb calorimeters. We see that we have a bomb calorimeter. It's set up. The the vessel holds it, and basically what happens is we have a reaction that takes place inside of the vessel, and so the volume's not going to change. So it's good for looking at that because we're dealing with our pressure and our temperature. So here's our equation. How did we get that equation? Well, again, we took our combined gas law, P1 V1 all over T1 equals P2 V2 all over T2. And what we see is since volume's held constant, we take it out of the equation. And we see that we have Gay-Lussac's equation right there. One thing we'll state here we need to know is that in Gay-Lussac's law that our pressure and temperature are directly proportional. So as one goes up, the other goes up. As one goes down, the other goes down. Measured in the same units, okay, that we've been using throughout all of gas laws. So let's look at an example. Example D1, it says a tank of oxygen has a pressure of 2.8 atmospheres at a temperature of 15 degrees Celsius. If the tank was left in the freezer overnight and the temperature dropped to 25 degrees Celsius, what would be the pressure? So the first thing we do, we see we have our P1, not V1, but T1, and we have our T2. We're searching our unknown is going to be our P2. So we'll go ahead and write all that down. So our P1 equals 2.8 atmospheres. Our T1, which we go ahead and take that into Kelvin, which that is going to be right around 288 Kelvin after we add 273. And then our T2, we add 273 to it and we get 248 Kelvin. Our unknown for this is our P2, so we're trying to figure that out. There's our given, our unknown. Our equation, we have our P1 all over T1 equals P2 all over T2. Remember, anytime we see fractions cross multiply, P1 T2 equals P2 T1. Okay, take this from here and we're solving for our second pressure. So we divide both sides by T1. And there's our equation. So we just go ahead and take this and plug everything in. So our first pressure is 2.8 atmospheres. And our second temperature is going to be 248 Kelvin, all divided by our initial temperature, which is 288 Kelvin. That's our equation. Go ahead, plug it in, solve for it, and we get a pressure of right around 2.41 atmospheres. And we see, does that answer make sense? Well, what happened to our temperature? Temperature went down, so pressure should go down. So yes, this answer makes sense.